Today we're going to be starting Unit 3, and in this unit we'll be looking at rational functions. We're going to start today with a little bit of review. We'll be looking at the reciprocal of a linear function. So for our purposes in this class, rational functions take the form p of x over q of x, or one function over or divided by another function. And when we divide two functions, what we end up with are not just simply straight lines or parabolas or those polynomial functions that we looked at in the first two units. When we divide one function by another, we do end up with some unique restrictions and some interesting behavior. We're going to spend this unit looking at that. But first, we want to take a look at the function 2x minus 3. This is a linear function. If we graphed it, we would get a straight line. We know this is a linear function because it's of the form y equals mx plus b. So we could tell just by looking at this function that the slope of the function is 2 and the y-intercept of the function is negative 3. The reciprocal of this function would be the function 1 over 2x minus 3. We want to spend today's video looking at this function and looking at how it behaves around some certain key values. So considering f of x equals 1 over 2x minus 3. Let's examine this and let's investigate, first off, the x and the y-intercepts. So first we'll find the y-intercept, and we get a y-intercept whenever the x value is 0. Find the y-intercept by evaluating this function at 0. So we can find f of 0. So evaluating, I end up with a y-intercept of 1 over negative 3, or more properly, negative 1/3. So our y-intercept is at the point 0 and negative 1/3. Okay, we can do the same thing for the x-intercept. We get x-intercepts when the y value equals 0. So here we'll be evaluating for when the function f of x is equal to 0. So as we have the equation 0 equals 1 divided by 2x minus 3. So we want to isolate x, and we can do that by first cross-multiplying, by bringing up the denominator. And when I do that, I'm going to have 0 times my denominator, which will be 0, and end up with this statement, 0 equals 1. Okay, and we know that's false. Okay, that's not true. 0 cannot equal 1. So in the context of what we're trying to do, we're trying to find x-intercepts. When we see a statement like this, 0 equals 1, which we know is false, then that means there is no x-intercept. This function never crosses the x-axis. Next we can think about domain and range. So let's find the domain of the function. Think back to grade 11 when you looked at these types of functions, and remember that division by 0 is not defined. So in our function that we're looking at, 1 over 2x minus 3, the denominator, 2x minus 3, cannot equal 0. So manipulating this algebraically, we know that 2x cannot equal positive 3, and x cannot equal 3 halves. So for our domain, x would be an element of the real numbers such that x cannot equal 3 halves. Just a question for us to think about. If x cannot equal 3 halves, what happens to the function as x approaches 3 halves? We can think of this two ways. We can think of this as x approaches 3 halves from the left, and as x approaches 3 halves from the right. Okay, so this is a little notation. Okay, that negative sign and that positive sign means something. This means as x approaches 3 halves from the left, and as x approaches 3 halves from the right. We can just make up a small table of values to illustrate what's happening for both cases. I'm going to pick some values that are getting closer and closer to 3 halves, or 1.5 from the left-hand side. And I'm going to pick some values that are getting closer and closer to 3 halves from the right-hand side. And I'm going to evaluate the function at these values. And you can do the same. So I've filled in my tables, and you can see as I get closer and closer and closer to 3 halves from the left, my function, my y values of my function are getting larger. And they're getting larger towards negative infinity. They're getting more negative. So as x approaches 3 halves from the left, my function, f of x, is approaching negative infinity. And as I get closer and closer and closer to 3 halves from the right, I can again see that my values, my y values, are getting larger. So I can say that as x approaches 3 halves from the right, my function is approaching positive infinity. It's getting larger. So let's ask ourselves another question. What happens as x approaches negative infinity and as x approaches positive infinity. What happens when our x values get very, very large and very, very small? So again, we can just set up two tables of values. We can make our x value get very, very negative, and we can make our x value get very, very positive. And we can plug these into our function and see what we get. So I plugged my values in for my function, and again, these tables are telling us something. As x gets very, very negative, and as x gets very, very positive, our function, the value of our function is getting smaller and smaller and smaller. It's getting closer to 0. So as x approaches negative infinity, our function approaches 0, and as x approaches positive infinity, our function also approaches 0. And both of these things that we've just looked at, this behavior as x approaches 3/2, and this behavior as x approaches positive and negative infinity, is telling us something. The value x equals 3/2 is something special. It's called a vertical asymptote. And the value that we saw when our x value gets very, very large and very, very small, that value y equals 0 is something called a horizontal asymptote. So we can put all this together and we can graph this. And I'm going to use the program GraphCalc to graph this quickly. I started with the linear function y equals 2x minus 3, and there you can see it in red. Straight line has a slope of 2, and it has an x-intercept, has a y-intercept of around -3. And I can also graph the reciprocal of this function, 1 divided by 2x minus 3. This is going to look a little bit different. Okay, this is a reciprocal function. I can see at -1/2, there's that imaginary line, that asymptote. And as I get closer to the asymptote from the left and from the right, I'm either shooting down to negative infinity or shooting all the way up to positive infinity. And as my x values get larger and larger and larger, my function gets closer and closer and closer to 0. So in general, when we're dealing with reciprocals of linear functions, our function will be 1 over kx plus c. And depending on the k value, if k is greater than 0, our function will look like this. It'll look like the function we just graphed. And if k is less than 0, it'll be reflected and look like this. We'll do another example in class tomorrow of graphing these functions, these linear functions. This is in your textbook, but again, to summarize, we have this general form. There's a restriction on the domain of the function, okay, because we're dividing. And then our function's either going to look like this if our k value is greater than 0, or our functions will this reflected function if k is less than 0. We'll also spend time in class working on these questions on page 153. If you'd like to start ahead of time, you're welcome to. Thanks for watching.